Welcome to tutorial 6, more pointers, where we step a little bit deeper into working with pointers. So starting to deal with how do you work when you have a pointer to a structure, and starting to do a little bit of work with the actual pointers. So to start the tutorial, you're supposed to consider first that you have a structure called complex that just has real and imaginary. So this is to represent a complex number as if this was math. You can see some examples here of how to actually declare that structure. So declaring it as blank or declaring it where you're initializing it automatically, knowing that the 4 first will go into real and then the 7 will go into the imaginary part. And you are now first off given a method called add complex that just does adding two complex numbers together. So you get two pass by value in, so it makes copies of all the data between these two structures. And then you have a sum here that is a pass by reference, so that any changes made to sum will be saved into whatever variable was actually passed in. So you can see it here where it's doing the work of adding those together. Your first part here for part A was to write a one-line segment of code showing a sample call to add complex, just this original way. So over here you can see again on the top shell I've got the code open, and in the bottom shell I'll be running it. And I have set up a C++ file just with that structure and the original method and a starting main. So you first need 3 parameters to it, and to make the call is just like any other function call. I am lazy, so I will just copy and paste and change it instead of typing it all out. And there you go. Well, I should compile this first to make sure that I didn't screw anything up. Nope. Okay, compiled, everything's okay. Even if we ran it, there's no output, so we don't see anything. So far as we know, it's okay. So we know that we have the structure, so this is one way declaring a blank one, declaring where we initialize right at the very beginning. We could also change some of the values, again, by going num1.real equals, say, 12, like that, which would change the real part right there of num1 of that structure. So where you're combining together a bunch of variables into one new type. But this is just that part A, to how to make a call. And so we know that the num1 and num2 are going to be passed in by value, so there's going to be copies that are actually made. But then sum is going to be passed in by reference, and we know that by the definition sum will contain the sum of the resulting actual addition. So when we come back from this method, sum will contain the addition of these two that we see right here. Okay. Now, just for fun, before going on, let's actually validate that this works right just by outputting the actual data. So I need to add in the IO stream. So just accessing the individual components from the structure that we have here for sum, and knowing that we should get 5 and 7 separated by a comma coming back. So let's go compile it. That's okay so far, and let's run it. Okay, good. We got what we expected, 5 and 7. So we're doing good so far. Now for part B, suppose the function is redefined so that it takes a pointer to the sum structure instead of using a pass by reference to pass the sum structure. The new specs of the function are, so you see everything from here, from structure, so we want to rewrite the header and the body of the function so that it conforms the new specification. So I've got to get this program to work the same as it did before. So first off is that we want it to accept a pointer instead pass by reference. And so remember, that's always the type and then a star to indicate now sum is going to be a pointer to a structure of type complex. When working with it now, we can't go the dot anymore because we're not working direct variable. We need to dereference it. So there's two things we could do. We could go star sum in brackets to first dereference and then go dot to access it. So that is purely legal. So we could do that for both. Right here, so that in brackets we are doing star sum to dereference that pointer first, and then once it comes back then it can work with it because we know, okay, by dereferencing it we are now at the type complex. But in C++ there's actually a different operand to use when you're using structures to make it easier, so you don't always have to put bracket and this star to dereference when you're working with structures or classes. Instead, what you can do is the minus sign and then the greater than sign, which creates an arrow. So it looks weird, but you have to think of it, it's sum and then this minus sign and then greater than sign to make an arrow, then real. And that's equivalent for doing it, and we can actually compile it. Compile it and dereference it. So for normal basic types like integers or doubles, you got to use the star to dereference that type of pointer. When you're doing it to something that's of a structure or a type class that you'll learn later on in the course, you can use what I call the arrow operator to dereference it. So it's just those two characters, the minus and then the actual greater than symbol, so it looks like a little arrow to dereference it. So this is purely legal here now too. Now what's going to be different is, again, now when we're calling add complex, we can't just pass in a complex and it's passed by reference. We actually have to pass in the address to the actual variable we want to use. So we use the ampersand symbol here now to indicate we want the address of sum to come out. So down here we've got sum dot because it's not a pointer, it's just the original structure, but coming back from this method, it should actually have been updated properly because we passed in the actual address and then dereference from the address to go to the object that was actually given. So it should compile again and give us the same answer we got before. Okay, compile correctly. And la-dee-da, same answer. But this time using an example of showing passing in and using pointers and dereferencing a pointer that's of type to a structure. And so C was to rewrite the sample call, so we've got that done and we have that working now as well. Now, is the pointer being passed by value or passed by reference? Now the answer to that one really is more is, remember that pass by value copies a value, or pass by reference gives a reference that's coming in. Now in this case here, we have a variable that's type pointer, and we are giving an actual address. And the thing is, we're not changing the address like here, we're passing it in and it's being copied. So this is actually a pass by value in this case because the memory address that is passed in right here is then copied and put into this variable. And if we make sum equal to a different address, it won't change anything for the variable that we see here. So this is only a local copy. But it still works to make a change to something that's external, because then when we take the local copy, it is an address to something that's external, and when we dereference it, we can still change the structure that's on the outside. So this is still pass by value. So should it be changed to be to the alternative, or is it this definition correct? Trace your calling stack. So everything here is still okay. Is one of the definitions of add complex better than the other? So doing a pass by reference or passing in an actual pointer? In this case, it doesn't matter. We really just wanted the result to end up in sum. If I was to personally code this, I would just do a pass by reference so that the caller doesn't have to guarantee that they're passing in the actual address. So that's as long as we're working with direct structures. If we were working with something that was dealing with pointers all the time and manipulation to a spot in memory, then a pointer would be good. But really, in effect, these cases are both the exact same. But this was to show you how you can actually accept pointer and values into a function to then access external data and make modifications to it, which will be important for future assignments. Okay, now part 2, and this is going to be the hand-in part of this actual exercise. And as usual, I'm going to go through it with you for stuff. We're going to kind of solve it together. You can either pause this or skip over it and try to solve it yourself first, and then come back and then watch the solution. But what you're going to have to do is hand in your code snippet that you wrote for this. For stuff. So you will find instructions where this tutorial is actually posted. But what we're going to do is write a function called Funnysort, which takes 3 pointers to integers as inputs. The function must sort the integers by swapping the pointers, not the values at which they point. So you can imagine here, this is a call and actually to the actual main. So we have the original variables here. We then have pointers set up to all of them. The Funnysort just takes those pointers. We need to compare the values and actually swap them in these variables. And then you can see this is being outputted right here afterwards. Okay, so you can set up this code. I already have set up a file. Right here. That sets up what you see here in this code. So having the actual main, everything else, make this a little bit larger so it's easier to see. Now right now I'm just outputting the actual star small with the pointers, but I really want to make a point that even when you're dereferencing these, it's accessing those original variables. So I am right now going to add in a new line, which also, after printing out the dereference of the variables, also prints out the original variables that you can see that the values have actually been changed. So small is referencing to x, so print out the x variable. Medium is right now referencing to y. And large is referencing to z. And these references aren't changed anywhere else. So once we come back out of this Funnysort method here, these will still be referencing the same variables, but the idea is that we've used the pointers to shift the actual data that's in these original 3 variables that's right there. So right now, this method does nothing, but I just want to compile it and show it beforehand and everything's outputting. Okay, you can see the original, we got x, y, z. You can see 7, 3, 10, and the first line with the actual pointers reference there is 7, 3, 10. So the pointers reference the actual data, then the actual data variables. So our goal now is then to write a method that would take any of these 3 variables and actually swap the data so that the smallest values. So right now they could be coming in and this is small is not the actual smallest, medium doesn't match. They're kind of random order. And by the time we leave this sorting function, we want out of the 3 variables that are here, we want the smallest value that's out of these 3 to be put into this variable, the middle value right here, and the largest value that's up right here. And so we're going to have to start doing some comparisons, and we have to do some swapping of actual data. So that if we find, say, like, hey, what if the current variable here, small, is containing a value that's larger than what's in the variable medium? Well, then we should swap the data. So what's in here moves over here, and what's in medium moves over here. And we're going to have to do this multiple times. So instead of just hard coding this multiple times, let's make a helper method. And so I'm going to make one that takes in 2 pointers, and it will actually swap the data that's in them. So you just give them here, so I'll call it void swap. This is a basic 3-step swapping that's needed, and so the idea is it's going to take whatever data A references to and it's going to swap it to the variable that's in B. So basically whatever these pointers, so not swapping the memory addresses of these pointers, it's swapping the data that they actually reference to, and it's not going to do any error checking. It's going to basically guarantee that these aren't null. If they're null, the program will crash, and that's a programmer issue to deal with, validating the data before coming in. So So first off, I need a temporary variable to hold some data so it doesn't get overwritten. So I'm going to dereference the variable a. So putting the star in front will dereference that for integer variable and go to the variable that it references, and it'll copy the data out and store it into temp. We then now can overwrite the variable a, so that the pointer that a reference, the data that the pointer a references to. So I'm not copying the addresses, but so putting star a, we are not updating the memory that's in variable a. We are going to the data that it references to, so the variable it references to, and we're doing the same thing for b. So I'm not copying memory addresses over, we're dereferencing it now, so we'll dereference b, go to that variable, and the data in the variable that it references to is then copied and stored into the variable that a references, right here. And now, we can do this, that, then copy the value from b, then we take the temporary variable, that data that we got from the original variable a, so that reference to, and storing that into b. So a basic three-step swap. Copy the data that a references, overwrite a with the data that b references, then overwrite b with the data that original a referenced. So that's a three-part swap that we will now use in the Funnysort method. Now the way I'm going to go about doing this is more the fact of, well, okay, well I need to make sure that whatever is the smallest. What happens if this is the largest? And I just want to compare them. So what I'm going to do first is compare, okay, I'm going to compare the small to the large variable, and we'll see, okay, if small is larger than that, right here, so if small is larger than what's in large right now, then I'm going to swap those two values. So just in case the smallest value is up here, so I'm going to swap them, that small would go into large, large would go into small. Next from there, I'm going to compare small to medium, just in case from right here that this then had something smaller than what was ever moved here. So medium will be solved here and then moved over. So either way, that's all I'm talking. Let's just start coding it and getting in here. So I'm going to do the first thing just to see what if this small right here is containing a value that's larger than what's in here. Then we should move them. So again, I want to dereference small because I'm not comparing memory addresses and comparing to the variable that it actually goes to. And if it's larger than what's currently in large right now, let's swap it. So calling our swap method. So we'll swap that data. And remember, this is going to be whatever actual variables are passed in. We're swapping the actual things that they reference to, not the actual memory addresses. Okay. So let's see what this does so far with our example. Because what we know is we have 7 and 3. So small will be 7 and large will be 3. And what we know is, okay, yeah, 3 is smaller than 7, so we should have this swapped over, and then 10 will end up being in the middle. So there we go, the actual output here. And you can actually see this from the original one we had before of having 7, 3, 10. Well, we still got 7, 3, 10. You know what would be really helpful while I'm doing this is to make sure I actually, hit save on the Funnysort. And, then that makes it easier when you're compiling there to get the actual values we're trying to go for. And then just to confuse you even more, as I'm the actual instructor, I realize I didn't even copy these values right here properly to match to what's in the tutorial. So this should be 10, so x should be 7, y should be 10, z equals 3. I please hope all of you still have faith in me at this point in time. I will finally get this right, matching up to what we see here and what we should actually expect. Okay, let's do it one last time. Okay, finally your teacher stopped effing up. Right here is that we started with 7, then 10, then 3. And so right here, that's small, that's large, and we can see they're swapped here, is then that's 7, that's 3, and then 7 is then been moved up. Okay, so we're not done yet. We don't know where everything could be. Basically, I'm just dealing with the first case of what if the smallest value here is larger than the actual largest from right here. I'm trying to go basically all different combinations of moving some of the actual data around. So we expect right here. So what happens is, okay, well, if large is bigger than small, nothing will change. But if small is bigger than large, well, then they would have been swapped. So we know in between that a smaller value being small than large. Well, what happens now if the medium is smaller than what's in the small right now? Well, then we should check that. So if small right here now is still larger than what's in medium, then we should swap those. So, you know, there could have been a smaller value that whatever was in large was actually smaller than what's in small, and so we need to swap that. But then even after this, or if nothing happened here, this was the smallest, but what if after this medium had something that was even smaller than both of those two? Well, then that should be an actual small, and then let's just shift it up. Now finally, the last thing that could happen is, okay, if we've shifted everything around, we got small and large, and we got 3 in here, is that, okay, if there was something small, would have been swapped over here to, in this case, but if medium was an even smaller, then after this, there's no case that we've compared here small against large and medium, that no matter what happens after the swapping, is small will have the smallest of the 3 values in there, no matter what. But what could happen after this is, well, what happens if the value that's now in medium is larger than what's in large? So we have one last comparison to do. Okay, let's see if that works for our example. So if we run this and everything is good, we have 7, 10, 3. We should see 3, 7, 10. Boom! We got it. And you can see here the interesting thing again is the pointers, dereferencing, that's that first output, are referencing these 3 variables, and we can see that we never changed x equals y anything else, but it is actually modified, and those are those pointers. So still from here. So again, this is just a basic 3-step kind of actual sort, and I do suggest that you actually do fully understand these steps and what was going on here for comparison. But again, we're just comparing out of the 3 data different combinations to end up with, do we actually have it in the right spot? So again, between the through of small to large, if small is larger than large, we swap them. So then this should be smaller. We then compare to medium, and if it's smaller, then they will swap, otherwise they won't. And so we'll get through either in 2 cases that we come through here and small was the smallest, there's no swaps that are done, or large was smaller or medium was smaller and the small will end up being down here. This last step then is just to see, okay, after everything's been moved, okay, is medium larger than large? Well, then they need to be swapped. And everything would be in the right kind of order, doing a basic kind of sort, and the comparisons for these 3 and needing to do the swaps going through it. And the other key one here is that we're working with pointers, so I am not comparing the memory addresses, I am dereferencing it, so the star going to the variable to compare it, and the same thing in the swap, it's dereferencing and actually changing them. So in the end, these 2 methods of swap and Funnysort are working with x, y, z because the original pointers that were passed in reference those actual variables. So some fun with pointers, and this is very important to actually practice this and understand this, especially coming up to future linked list code and then doing any low-end kind of code. And a good way to do this, if you're a little bit confused, is to draw out the memory maps. Like, I won't do that here, I would like you to do that. But what you should do is trace through this. Set up the memory maps like you've seen before in previous tutorials, and then follow through the actual execution of this entire thing and see how it changes for the overall data. We can even go through and maybe modify some of these. Like, hey, let's even test this right now. Like, let's go the complete opposite of 1, 2, 3. We're right here, so it should be 3, 2, 1, and we should see an output of 1, 2, 3 that's properly sorted. Yep, 1, 2, 3. We can even change it around here of 2, 1, 3. Different combination and see. Yep, still getting that correct sort. So we got all of that working. Now, one last little thing for this tutorial, so a little bit faster to give you extra time. We just have one last little trace to kind of step through. I won't run this. So the program segment below contains at least one error which will cause or is likely to cause a runtime crash. So when the program's running, it'll crash. Something like maybe a segmentation fault. Draw a picture of memory and update it as you trace the code to try and find the errors in the problem. So I'm still going to leave this for you to do, but I'm going to step through this from my experience and see what are we working with. So this code is working with that original complex structure we had in the very beginning, and assume that this is then in the code in the main, and then this is a different function that we had here. So we start is we have one structure here called F1 with the data 3, 5. We have another structure here called F2 with the data 17 and minus 1. And then next we have complex star sum. So this is not an actual structure. This is going to be a pointer to a structure, and it's not initialized anything. So by default here, this is null. That's going to be very important. We then have the add complex. So F1, F2, and sum invoked previously for our definition that we originally had. So I'll bring that up here. So this is that new one that we actually had, and this is the definition that we had here. Boom. So this is the complex star. Now that's going to run. Then after this, you can see the output. Then it's going to do write complex, passing in the actual address F1. Then we have this output F2, and you can see it's passing in the address. Then the write sum, and you can see this method down here takes in a pointer to a complex structure and then outputs the actual data using then that dereferencing that we've seen before that looks like a little arrow. Now to step through this, we have to see, okay, well, what's going to happen? So, okay, well, we got the memory. This is going to create an actual structure. This is going to create a structure. This is going to be null, so not reference anything yet. Then we go to our add complex, which comes here. And okay, well, F1, F2 to add those. That's passed by value. That's okay. Here, this is a pointer. So the address that's in this one will be copied over to here. This is pointing to nothing right now, so basically being null. So this will be null. We come here and we go sum arrow real. So that's the problem. We're dereferencing this pointer, but this pointer right now is pointing to null. That's what was passed in, and that's not possible. That means it's to an address that doesn't actually exist, so the system will crash the actual program. So this line here will cause it to crash. Now there is another error, so even if we didn't have any of this causing any problems from this original right here, you also have the write right here, and you can see that, okay, well, this one, F1 and F2 are actual structures and we're passing the address, so this will work. But then this right here of sum is still null. It hasn't been updated anywhere. Like this add complex won't update that. It's not actually allocating anything right here. And so for the sum, even if this wasn't here at all, we just didn't have that line, we were going to go on to here, by the time we get down to the write complex, it's going to come in here, we're going to go here and go c-real and realize, well, this is a pass by value, so the address that's here is copied in, so sum, which is set to null and hasn't been changed since that point in time. We come in here, null is copied here, then we go and reference that's holding an address to null, try to dereference it with the arrow there, and it's going to crash. So this is a case of trying to dereference on null is the actual runtime. So this will compile, but sure as heck is not going to actually work properly. We can even test that to see it running here, is that if I don't even have the add, I don't do anything right here, and we see we changed now that this is a star. So even here having a star after that, just the exact same like sum. We're not doing anything else. It's a pointer. It'll default to actually null right now. And let's even just leave the add complex we had before. In this case, we don't have to the ampersand to pass it in. I'll just copy the address. This should compile. Okay, that's just a warning. Boom, crashes it. You can see segmentation, core dump. Right there. So boom, that's not good. That caused an actual issue. because we're trying to go up here and we're trying to dereference it. So I can even show that again by not even calling this method, but just trying to even work with sum right now. So it's not sum, like sum equals is valid to do because we're overriding an address to something, so we could say sum equals num1 and give it the address, and that's perfectly okay and that's legal to do. But the problem is when we try working with the pointer that's not referencing to anything yet for the actual address. So set up, so even if I just try just to do that, like just a simple statement like this, not even doing an assignment, let's say even like whatever, we'll try to assign it to 3. We're even giving the arrows right here beforehand that this is causing issue. That warning sum is used uninitialized in this function, still called core dump, so it's crashing. Same thing would happen here. So happens here if we're using original call, but even if that call wasn't there, it would happen anytime from that first line right there that we started going into the actual function. Okay, so this is a shorter, so just over 30-minute kind of tutorial, but please don't rush past this. Like this spending time to understand pointers is going to be very important for an upcoming assignment and for your midterm, and just in general with dealing with low-end code. So sit down and make sure you understand what pointers are. Make sure you draw out the memory, because that's very important. You can't just skip over for this code without trying to draw and visualize what's going on in memory. If you can see it in your head already, go ahead, that's okay. But if you're having troubles visualizing this, we'll draw it out like we've done previously. Other than that, please continue to be the awesome people that I know you are. And as I always say, if you think you're not awesome, you're wrong. I'm right. Have a good day.